Okay, so now let's look at some applications of multiplying vectors, specifically in physics, and more specifically here in physics C mechanics. Okay, I'll mention a couple E&M formulas at the end, but these are specific examples for the mechanics area. So the concept of work in physics is one area in which we use a dot product. And so the formula is work is equal to F, the force, times, or dot, right? So F dot the displacement, okay? And so the more common way to write the formula is just F delta X cosine theta. So one thing to note, work is a scalar quantity, okay? So remember, dot product is a scalar product. So when I multiply all this out, I'm going to end up with a scalar in the end. Again, signature of dot product right there is this cosine theta, okay? And so here's an example. You got a toy wagon is pulled by exerting a force of 25 pounds on a handle that makes a 20-degree angle with the horizontal force. Find the work done in pulling the wagon 50 feet. So we're going to do work equals force dot delta X, so F dot displacement, the force dot displacement. So it's going to be F delta X cosine theta, and so we're just going to plug in numbers. So it's going to be a force of 25 pounds. I know these are the US customary units, but it's okay. Our unit won't be joules in the end or newton meters in the end. It'll be something different, okay? So you got 25 pounds exerted for 50 feet at an angle of 20 degrees. And you get approximately 1,200 foot-pounds, right? This is still a unit of work because it's force times distance, okay? Now, the next one involves what happens now when you're looking for the angle, okay? So the work done on a car that is towed by a cable that makes an angle of 25 degrees is 2.9 times 10 to the 6 joules. The car travels a distance of 2 kilometers. How much force was exerted on the car during this trip? Make sure you convert this to meters, right? Because remember, a joule is a newton meter, newton times meter, okay? And so we want to eliminate the meters, all right? And so now we're going to use our work formula, right? Work is the dot product of force and displacement, okay? Or F delta X cosine theta, right? And so if I solve this now, I'm given the work, I'm given, right? And so this is the one thing I'm looking for. So F equals F dot delta X, which is our work, over delta X cosine theta, right? And so we're just going to do 2.9 times 10 to the 6 joules divided by 2,000 meters cosine 20. Oh, sorry, 25. 20 was the previous answer or question. Okay, which is going to give us approximately 1,600 newtons. All right, so there were 1,600 newtons applied during this amount of work done. Now, if we look at the other one here in physics C mechanics for cross product, it's torque, right, which is given the symbol tau, which is a Greek letter, the Greek T, okay? So it's an area of physics that uses cross product. The formula is tau equals R cross F, right? So when you do cross product, it does matter which comes first, which comes second, okay? Because if I didn't follow the right order, I would end up with negatives and so forth, okay? And so that's just simply RF sine theta, right? And then we'll just call it K hat because it's generally going to be in the Z direction, remember, and so forth, okay? And so let's look at how this is used, all right? So here we have a force of 6 newtons exerted at 30 degrees to a wrench at a distance of 8 centimeters from the nut. It is just able to loosen the nut. What force, F, and for some reason I had 2 F's here, would be sufficient to loosen it if it acts perpendicular to the wrench at 16 centimeters from the nut? Okay, so the first thing we need to do is find out how much torque is applied. Right, so tau is R cross F, or RF sine theta, right? And we have our K hat, right? So that's going to give us the direction. And so what we're going to do is we're going to plug in our values. So it's going to be 6 newtons exerted at 0.08 centimeters cosine 30. And so we have a torque of 0.24 Newton meters, okay, that's needed. And now we're going to take this information and solve for the force required, okay, if we apply it perpendicular, now 16 centimeters away. So we're going to solve for F. So F is going to be R cross F, or our torque, times R sine theta. So R cross F was our answer that we found before. Okay, so it's 0.24 Newton times meters. We're applying it now at a distance of 0.16 meters away, and perpendicular means sine of 90. Okay, sine of 90 is just going to be simply 1, so we're going to divide 0.24 by 0.16, and it's going to tell us that we apply a force of 1.5 newtons to loosen it. And so you can see how much less you have to apply if you're further out at perpendicular versus the first one. We had to apply 6 newtons and we were only 8 centimeters away from the wrench, but we were applying it at at an angle of 30 degrees, okay, which means that not all the force that we were applying is going to apply to the nut. Okay. All right, next one. What is the torque of the force F equal to 2I hat minus 3J hat acting on the point R, which is R, the vector R equals to 3I hat plus 2J hat about the origin? Okay, so one thing to note, okay, because when we did the cross product video, we talked about how most of them are going to be 3-dimensional. So when you only have 2 dimensions, okay, so when you only have 2 dimensions, right, you're only going to do the z calculation. You're going to find CZ, okay, because when you do the formula, right, so when you do that, you're only going to do, so you're only going to calculate CZ from our previous, right, because before we had CX, CY, CZ. So you're only going to find this CZ, which is the perpendicular component from R cross F, okay? Another way to think about it is if I look at my vectors, I have 2I hat minus 3J hat. Well, the third dimension would be 0K hat, right? And same thing with R, right? I would have 3I hat plus 2J hat plus 0K hat. But if I plug, remember, CX and CY all have the Z direction. Okay, so which means I'm not even going to worry about that. And so what I'm going to do is I'm going to do torque, right, is R cross F, which for us in this case is going to be Rx Fy minus Ry Fx K. Okay, and so that's going to be 3 times negative 3 minus 2 times 2. All right, so it's going to be the magnitude K hat, and so that's going to be a negative 13, right, Newton meters in the Z direction. Okay, so that'll be the torque that is applied to this point about the origin. Okay, all right, so now this just kind of wraps up. So I only showed you a couple examples of dot products and cross products. A couple other cross products that you could run into called Biot-Savart law. I always forget how to say his name. But this tells us the magnetic field around a point charge, and it's a cross product. So it's mu0 over 4 pi times QV, where V is a vector, cross R, which is a position vector, over R squared. So you can see that cross product, so you can rewrite that with a sign. And then another one is the force on a current carrying wire. Okay. Which is force on the wire is equal to the current times the length vector cross the magnetic field. Okay, so those are just two other examples of cross products. And again, there's more dot products. Sometimes you'll take the integral of the dot product. Sometimes you'll take the integral of a cross product.